start the afternoon session of this glorious reinforcement learning day. So we're very happy to have Dale Schuurmans from Google, policy optimization.
Okay, thanks. So maybe to set the context a bit, I'm going to try something actually quite simple. So this is not a theory presentation. There will be, a theorem or something, but it's not really the point of it. I think the point of what I'm trying to do here is sort of advertise, I think, a lot of missed opportunity, both algorithmic and theoretical, really down in the sub-basement of reinforcement learning. And I think, well, actually, maybe I'll just launch into it. So let me sort of establish context by starting with this big picture. We all know this picture. This is the single most dangerous picture in all of AI. The reason this is a dangerous picture is it makes the reinforcement learning problem look so simple, right? There's just these two boxes, a couple arrows, agent environment. Seems like this should be an easy problem. And the deception here is that in this picture, you can embed, pretty much all of AI. You can embed a staggering array of very complex, very difficult subproblems. And I have to admit, I was supremely impressed this morning with a lot of the theoretical progress on tasks that I'm going to shortly show you are sort of at the middle range of complexity in the story, that may be even overreaching beyond some of the more basic things that I still think we haven't nailed down. So here's what I mean. Imagine if you're a reductionist and we want to start to decompose this overall problem into a couple of sort of key tangible subtasks. Well, here's an attempt at breaking it down. When I said agent and environment, I didn't say anything about the environment. For example, the environment could have other agents in it. The other agents could be aware of the presence of your agent. There could be things then that happen like non-stationarities due to coalitions and cooperation and competition. Normally, when we put that diagram up there, you're not even thinking about that, but multi-agent interaction is indeed an overwhelming challenge. And it's not even clear in all cases what a solution concept really is that we should be seeking there. If you eliminate that and say, no, it's a cold, oblivious universe to the presence of the agent, it's just got to deal with physics, we still have the perception problem. The partial observability task could be a very complex universe. So our agent needs to now construct memories to allow it to disambiguate its current perceptual state from situation. In your mind right now, your context, all your commitments, things you need to know, and so on and so forth, are not listed in front of you. They're constructed memories based on your past experience. These are the critical memories you need to build in order to act effectively in the universe. So partial observability is an acknowledged, well-known difficult problem. What I've started to realize, though, is that like textbook reinforcement learning, the thing we presume we're talking about, Markov decision processes, is at a pretty intermediate level of complexity. And I'm pretty impressed with the heroic efforts to understand how to solve problems at this level and everything below. But I want to kind of take us down a level. So what's interesting is that batch reinforcement learning is somehow now an emerging problem, where what we do is we take sort of the Markov decision process problem and we remove the responsibility of the agent to deal with the exploration-exploitation trade-off. Simply an exploitation problem. Perhaps we give you data or a simple model, and we just ask you to produce an optimal behavior strategy. Even here, things are not that simple. For example, we immediately encounter the temporal credit assignment problem. Perhaps in data, you have to now figure out or attribute, which of the sequence of decisions were the critical ones, if any or all. That's in the retrospective view. Prospectively, we now have to deal with this kind of short-term versus long-term trade-off in reward. I'm actually going to mostly talk about the thing that's below that, beneath our attention. The pure policy optimization question that comes up when we're not even dealing with Bellman consistency concepts, but just straight out optimization and one-step decision making. It's at this level, actually, where most of the connection to the rest of machine learning resides. And I'm going to try to make a case that a lot of the obvious connections are really fruitful here. And they're kind of missing in most of what we're thinking about in this area. So I just want to kind of close the gap there and see if I can inspire some additional work at this level. I will come back up to sequential decision making at the end and try to explain a bit about what we're thinking there based on what we can understand at the bottom level. Okay, so I'm just going to start out by actually doing this in a very simple way. Here is a very basic problem that actually students to the field probably are presuming we already know how to solve. It's the batch policy optimization problem in contextual bandits. So imagine I just give you a set of data or a set of contexts like x1 to xm, where let's even assume they're IID, context from some stationary distribution. Let's simplify further, assume we have like a finite set of actions, a1 to an, and our data consists simply of the natural thing, which is, in context 1, we tried action A2 and we saw reward 1, and that's all we saw in context 1, and so on and so forth. So we've observed one action in each context. And our task is simple. We just, on the basis of this data, need to produce a good policy. One moment. And what do we mean by good policy here? Well, let's say what we mean is what we mean in the rest of machine learning, or at least classical supervised learning, is we're interested in a policy whose expected reward on future data outside of this data set, right, is as high as possible. So the generalization question is the central question in this picture. And yep.
So just to make sure I understand whether you're sort of more in a causal type setting or not, do we know the decision rule that was used?
Yeah, it's coming.
Okay.
Yeah, at times yes, at times no, but it will be clear from context. So anyway, just to kind of build up intuition, so yes, I think that there's these basic issues that we face here. Actually, this problem is quite subtle. So maybe just to, again, engage your intuition a bit, by optimizing, say we have a parametric policy class, by manipulating the parameters of that policy class, what are we doing? Well, we're changing the policy. Changing the policy is essentially, in this data, shifting the mass, into various different, column locations in each row. So what we want to do, when we're training, at least we think about, is how are we shifting the mass, the policy support, in this data set, to maybe land on high reward, high observed rewards, maybe avoid low observed rewards, and you can start to see there's a lot of risk here and there's a lot of subtlety. For example, if all the rewards are the same, that's not interesting. Maybe you simply want to move all your mass onto the observed data. Well, that's simply just relearning the behavior strategy, assuming there was a stationary behavior strategy, assuming that it was a good strategy, and I never said it was a good strategy. Ideally, what you want to do is actually, optimize the policy to do better in expected reward than the data collection mechanism. Okay. Yeah. One moment, Isha. And so, in the extreme, you might say, well, there's a largest observed reward here, right? We want to move mass onto that, and may even sacrifice moving mass off the rest. But you can see the danger, which is now, if we move most of the mass off the support of the data, we have almost no statistical evidence to support like any inference we want to make about the quality of that policy. Yeah.
Quick question. So first of all, for the context, our policy does not influence the context. Is it
No,
so?
it's IID. That's right. No sequential.
Now, if I would like to make a much simpler model and say full observability.
It's coming. Yeah.
Oh, sorry.
Yeah.
I should have expected it.
Okay. So here's what I'm going to attempt to do to organize the discussion. Is I'm going to focus on these two sort of sub bullets here, which is normally in machine learning we'd think about like an optimization process to optimize the parameters of the policy. Okay. So I'm actually going to go in some depth about how we consider what the optimization objective should be. And then the other obvious issue here is the missing data problem, right? Like we have all of this, missing data, and how are we reasoning about that missing data, or, what inferences we're making explicitly or implicitly about that missing data is actually quite essential. Okay, now before I actually start decomposing this, there is an elephant in the room, and it's kind of like the default answer. There's another one, but this is sort of the first primary default answer, which is we already know how to do this, right? All we got to do is like assume we've logged the behavior, the proposal probabilities of whatever the data collection process was, and then simply do a simple importance correction, like recorrect, dividing by the inverse, multiplying by inverse propensity, the policy probability times reward. That gives us an unbiased estimate of expected reward. Expected reward is what we want to optimize. So we've answered both questions. We know what our optimization objective should be, and we know how we should be dealing with missing data. This research was motivated by the observation that this is a very poor answer to both of those questions. And if this is a poor answer to those questions, what might a good answer look like? And what is surprising is in both cases, better answers to this question are already well known and things we already have studied quite a lot in, for example, supervised learning and other areas of machine learning. So I just first want to connect this up to things we already know And we already understand better ways to approach this problem if we just simply connect the dots. Okay, so let me start with the how do we formulate an optimization objective or a reasonable principle by which we want to tune the policy parameters. And then I'll get to missing data. So first, optimization objectives. So yes, indeed. So to isolate the task, let's simplify it, okay? Fully observed data. So I give you a complete table. We've seen every reward counterfactually for every action in every context. And we're interested in maximizing the expected reward. Now, I'll remind you, what we're interested in is not the expected reward on the data. We're really interested in the expected reward in future data. But, you know, this is sort of our target objective. And we could imagine now, without even having to do importance correction, that this is all we, you know, problem solved. This is the objective. And we just optimize this, okay? And the observation is that we've missed something here. And it turns out, and actually, Alec already pointed out, that this is a fundamentally poor optimization objective. It's actually an incredibly bad way to train your policy in the fully observed case. So there's no variance to deal with here. And we're in trouble. And I was going to explain why we're in trouble, but I think Alec already explained it, is that normally when we parameterize a policy, we're going to produce some mapping, you know, some neural net or something that maps context to a score vector across actions. That gets converted to a policy through the softmax transfer. We exponentiate scores, we renormalize, produce a probability vector. That's the policy, okay? The problem is here that, oh, sorry, I thought I had this. This inner product between the reward vector in a given context and the policy probability vector in the given context has to go through this softmax. That inner product and that softmax transfer interact incredibly poorly. For example, it plateaus, right? So as you concentrate your probability mass on an arbitrary action, not even a good one, the gradient goes to zero. The landscape flattens out, okay? You can even do fun things like make it worse. You can also embed like local maxima all over the place. You can create interference patterns. You can embed like exponentially many local maxima on this surface. It's in fact hard to create a harder optimization surface that's still smooth. It's differentiable. It's plateaus everywhere, and you can create like, you know, arbitrarily complicated landscapes. It's nearly impossible to train this objective, even in this fully observed case. Yeah.
I mean, I'm kind of quite ignorant about reinforced learning, but coming from supervised learning, I mean, this looks like ERM worrying about fitting to the training data and not about generalization to future data.
Yes, that's true. It's also ERM, where we're using misclassification. Coming to that right away. In fact, that's the next thing I want to say is we already know we don't train this way in the fully observed case. And what I mean by this is, well, let's imagine we look at a further special case, which is, what if it just so happened that the rewards are 0, 1 rewards, where there's a single 1 in each column, which is a correct class label, right? So you get a reward of 1 if you get the correct class label, reward of 0 otherwise. Now our expected reward objective is classification accuracy. Okay, and how do we train a supervised model to, you know, both fit in terms of classification accuracy and perhaps generalize to new data? Well, what we don't do is optimize r.pi. What we do, and what we teach all of our students to do, is to maximize r.logpi, not r.pi, right? We use surrogates. In fact, we use it so often, we don't even think to not use surrogates. And what's remarkable here, of course, is that r.pi objective is perfectly differentiable. Like you change one, you know, you change your loss function in TensorFlow, you rerun the experiment. There's nothing preventing you from doing this, other than the fact that it just doesn't work very well. It's a, you know, intractable optimization. We, on the other hand, by looking at log loss, what have we done? We've created a surrogate objective that is now convex, at least in the top layer, the score layer. It is actually related to the original misclassification loss that in the, you know, if we have enough capacity, the global minimizer, if you can reach it, in the r.logpi is the same as the global maximizer in the r.pi. So we preserved the global maximizer. We've now created a convex optimization surface. This is such a natural thing to do in supervised learning that we have forgotten to remind our students that when we're measuring misclassification error on training and test data, that was the target loss that you could have chosen as a training loss, but you don't choose that because it's untrainable. Okay. What's remarkable to me is to see that this lesson now is instantly forgotten the moment we start to remove some of the data. Okay, anyway, but just to close the loop on this, so we understand in supervised learning you use surrogates to make the training problem reasonable, and yet still we have a fully developed like generalization theory and so on and so forth. So it doesn't preclude reasonable theory. Just for the sake of argument, I ran the experiment. The yellow line is training with expected reward, and there's plateaus and hills. Actually, the other way to understand the difficulty with the r.pi objective through the softmax transfer is when you look at that softmax transfer, if you had a temperature parameter where you took scores divided by temperature, then exponentiated and normalized, take that temperature in the zero temperature limit, your landscape is now piecewise constant, right? So it really is plateaus everywhere, zero gradient everywhere, and then you're just searching this hopeless, combinatorial landscape. All that's happening by moving the temperature away from zero is that we're adding a little bit of shape, but it turns out the real optimization landscapes are virtually plateaus everywhere, and you can see here, you're caught in some plateau, you think it's converged, and then out of nowhere you drop, and then you're caught in some other plateau. And I've run this only goes up to 200, I've run this thousands, like it never succeeds, right? It's just lost forever.
Question.
Yeah.
So you've added a log, is it just a policy gradient trick?
It looks the same, but the policy gradient trick is relying on an on-policy distribution, and this is, by the way, going to be all off-policy. But yeah, it's related. Sure, the answer is yes. Okay, so okay, let me just sort of close the loop in the general case. Of course, we kind of know what to do in the 0-1 reward case, which is we just do r.log pi. But what if R is general, like not 0-1 loss? It isn't much trickier, but actually that was sort of a more recent finding. So Chaba and Bernardo and I think others have shown that indeed you can construct convex calibrated surrogate objectives for the general cost-sensitive classification task. What I just wanted to share with you briefly is that actually once you start thinking of constructing surrogate objectives, it's pretty easy to come up with reasonable ones. I happen to like this kind of entropy regularized trick, which has already come up several times today. If we look at expected reward, we just add a bit of entropy regularization with a tau parameter. We have biased the results, okay? The optimal policy has now been shifted away from a one-hot, like a deterministic policy, to a slightly more diffused one, but the bias can be completely controlled by tau. What we gain, though, is a really intuitive, natural access to a whole space of plausible, reasonable, effective surrogate objectives. For example, if you have entropy regularized expected reward, that is equivalent to minimizing a KL divergence between your policy output and an implicit probability, a target distribution that we never mentioned, but I think it came up this morning, which is simply the exponentiated reward distribution. So, for tau regularization, optimizing the top objective is the same as, creating an artificial target distribution by dividing the rewards by tau. This is still fully observed. Exponentiating, normalizing, calling that a distribution, measuring KL. Okay? Now, this has not changed the landscape problems, but by looking at it from a KL lens, we now see really, really obvious ways to develop other surrogate objectives, like, for example, flip the KL around. Flipping the KL moves from something that is like, entropy regularized expected reward to something that looks an awful lot like supervised, like log loss. And in fact has much the same character. It is now like convex in the output scores. It's also unbiased in the sense that it has the same global minimizer as the original objective. So we've introduced convexity to the landscape. We've preserved the global minimizer. We want to preserve one other property to prove some theory, but basically it's a cheap and easy way and natural way to produce surrogates. Just quickly on the side, I want to pose it as a question to the theoreticians. Quickly on the side, if you took this and we went back to the original log loss case and we compare these two objectives, we'll notice that this reverse KL is very similar but not identical to the original r.log pi, the maximum likelihood objective. The difference is simply that in the maximum likelihood objective, we have our score vector Q being inner product with the indicator of the correct class label. And here, when we do the reverse KL, the only thing different is the inner product is with respect to this implicit P, which is take that indicator vector, divide by tau, exponentiate, normalize. That P distribution is not deterministic, right? It actually has mass everywhere. And so all that this has done is smooth the labels. This was a discovery a few years ago in like mostly an object recognition context that smoothing the training labels in maximum likelihood for whatever reason is giving a generalization boost. I'm aware of no theory that's justifying or explaining this, but it's actually a pretty persistent, although somewhat small, advantage that people are relying a lot on practice these days.
Well, one theoretical explanation is that if you view your labels as being generated by some target function, you're simplifying the target function by smoothing it. So that's,
And then you turn that into a theorem?
yeah, yeah. No, it reduces the number of the minimum norm solution, so it's, yeah, it's a theorem.
Cool. Yeah. Cool. Okay. Let's see here. One further step is to get upper bounds, like to get like sort of risk bounds and sort of generalization theories. It's nice to have upper bounds on the target objective. So if we said the entropy regularized expected reward was a target objective, we can also now construct calibrated convex upper bounds on that target objective. And that will come back later. That's sort of a useful widget. These made-up objectives actually work quite well if you just sort of replicate like the text, the sort of the machine learning demo 101 scripts, and then just plug out log loss and replace it with expected reward. That doesn't work, but if you do these surrogates, indeed, you can train pretty rapidly and you get generalization benefits in a bunch of different contexts. So in practice, this is just connecting to what we already understand in supervised learning, and it's beneficial. Okay, so now let's go back to RL. So next step is, well, what if the data is missing? So in some sense, if we're looking at this batch contextual bandit optimization task, the only difference between what we're looking at here and classical supervised learning is simply the missing data problem. And so I think the other interesting question is, in RL, what tools, what thinking, what techniques were we bringing to bear about reasoning about missing data? And from where I'm sitting, the answer is kind of depressing. Mostly what I'm seeing is, let's start out with very trivial strategies. One way to deal with missing data is like imputation. So you can imagine you have a model, maybe you've trained it somehow, and you just simply use the model to fill in guesses for all the rewards you haven't seen, right? Reduce the problem to a fully observed problem and then deploy whatever previous techniques and theories that we already had in hand, okay? This sounds naive, but actually this is the foundation for what's going on right now in most approaches. And what I mean is, just let's look at, for example, importance corrected expected reward. If you look at importance corrected expected reward is mathematically equivalent to taking that data, filling in 0 for every guess, for everything you haven't seen, taking the things you have seen and exaggerating them. Okay? That's what it does. That is probably the worst missing data inference technique I've ever encountered. It has one benefit though, is that it's unbiased, right? By putting zeros everywhere and by like exaggerating the things we've observed, when we think about expected reward vectors under the sampling mechanism, right? Well, sure, we'll multiply by the proposal probability, we'll cancel out the thing we divided by, we'll now instill this one hot vector on the observed action times the reward. When we add those up, we get the original reward vector. So it's unbiased. If you're trying to prove theorems about expectations, it makes a lot of sense, right? It simplifies your life. But in terms of actual technique, right, how you're actually going to train a policy on this data, I'm sorry, this is committing to pretty weak technology. Yeah.
But you can get high probability bounds also, right?
Yeah.
Yeah. Okay. No, but okay. The other question is the other technique. Okay, there is a huge difference because here someone gave you the betas, and if someone doesn't give you the beta,
that's harder.
I have no idea how to get around it. Maybe you have.
Well, what people do is they fit. They'll presume it's from some stationary policy, and then train another policy to fit that policy, and then use those, and then argue about the the bias that you introduced by the fit. Okay. Anyway, that's not the point I'm trying to make yet, but that's cool. There are, some obvious improvements. One is, okay, I'm not addressing the variance issue here, so this is obviously high variance. There are a lot of sensible, sophisticated variance reduction strategies. But I actually want to persist by drawing connections to the rest of machine learning. But one intermediate step is, a mild improvement, which is to actually use a model other than 0 to fill in the missing data. And you still can recover unbiasedness rather simply by just still exaggerating on the observed components, but not exaggerating the observed values, just exaggerating the difference between the observed value and your guess, your model prediction. Okay? It is better in terms of variance. It's still unbiased. It's not that much more sophisticated, but at least it's certainly better than zero. This, however, allows us to think a little bit about basic reinforcement learning techniques and how they relate to machine learning as follows. The model has to come from somewhere. And so you ask yourself, the question is like, where does the model come from? And it seems like people want to naturally run into this kind of two-model view where, while we started with a policy, some parametric policy representation, that's the object we care about, that's the thing we're trying to produce. And now we need a model to fill in the missing data. That must be a different model, right? Because it's doing a different job. It's guessing rewards instead of like producing probability vectors. But if you think that way, then what happens here is that, well, where does that model come from? The most natural thing is, well, this is the only data we had. That model's trying to predict rewards, so the natural thing to do is just regress that model to the observed rewards and then use that as the predictor. The problem is if you take that model now, we already know what the optimal policy is for that model. It's either like the greedy policy induced by that predictor or maybe a softmax, like an entropy regularized version of that policy. But actor-critic thinking in this one-shot decision-making scenario is virtually vacuous. First of all, the value function is policy independent. It's just the reward function. So basically, your critic is just learning the reward function. You could imagine trying to iterate with some policy improvement. You do your policy improvement, and now it's the same reward function. You're at a fixed point. Okay? And if you literally take that model and use it, this is the direct method. It's not bad. It often does better than importance correction, but it's actually not an effective technique, both in theory or in practice, to just do least a simple regression to the observed rewards and then extract a greedy policy from that. Okay, so here's where there was an opportunity that I think we're missing, and I'm trying to somewhat advocate, but it's hard to get people to. Anyway, let me try it. Is what if instead we just go back to thinking like there's only one model, right? There's just this one object we're trying to produce. But once we've already kind of accepted that there's some kind of relationship between score vectors and probabilities, that maybe we could just unify the models and say we have one model that simultaneously is a reward estimator and a policy. Okay, and that same model, like it just depends whether you look at the model output before or after the final softmax transfer, but it's just that one object. I would argue you gain a lot by unifying things in this way. In particular, we now can merge some of these missing data inference techniques like doubly robust estimators with the previous surrogate losses totally seamlessly. Maybe it escaped your attention previously, but these surrogate objectives that we had before, we're working both in the space of logits and in the space of the output distribution. So it was unified before, nobody noticed. There's just one model being optimized, everybody seemed happy. And now I remove some data and suddenly we want to have two models. And I'm just pointing out we can go back to one model, it's still coherent. And in fact, it's sound. So I'll try to argue a little bit that this isn't as made up as it seems. This at least allows us to think like fairly flexibly about surrogate training objectives, perhaps motivated by the fully observed case, and combining them with like reasonable missing data inference techniques. Fit them together, they come together in one model, and you get an optimization objective you can optimize. Where, for example, you can use like self-imputation strategies to fill it. Okay, this works amazingly well, at least in the sort of the typical scenarios people like start looking at. But what I want to point out is that it is actually sound and in some sense. And I'm not going to, this isn't a theory talk, so I don't think I'm going to drag through everything, but you can take, this convex upper bound as a surrogate objective. You can look at the empirical version of that upper bound. We can define our target objective as the expected smooth risk, and by smooth risk, I just mean the entropy regularized expected reward. And indeed, it's just a textbook exercise to apply things we already know, that as long as, certain boundedness things are, assumed, and we use an unbiased inference mechanism. When you combine these things, you can show, yes, with high probability, if you get a small empirical like surrogate risk, that does imply with high probability a bound on the true gap in the, in terms of the expected smooth risk. Okay, so it's not, not completely arbitrary. It allows us to actually just apply machinery that we already have lying around. Yeah?
So I'm just trying to parse the circuit loss a little bit. One thing I'm not fully understanding is the squared norm that you have is, it cannot be, what exactly is the norm across? It cannot be across all the actions because I have missing data as you're pointing out. So is it a norm over context? What is the space?
It's interesting in a lot of areas of machine learning right now, when people complain about non-differentiable objectives, what they mean is missing data. Yes, so this is actually over the entire vector, but what's being used here is a missing data inference mechanism. So it's a combination of both. So I pick an objective for the fully observed case. This is a pretty naive approach, but anyway, I pick an objective from the fully observed case, and now I have a bunch of missing data, and then I apply some missing data inference mechanism that fills in guesses, and I just compose those two operators. And
Think of R as an estimated reward vector that has already filled out all the missing.
yeah, there should probably be hats on it and so on. Yeah, so the way you apply it is you produce an R hat vector. And then, compose it.
And the other thing I was trying to understand, like, okay, your theorem is right now, as pointed out, informal, but where does actually the properties of the data collection policy show up?
Yeah, they're definitely, so beta is like, there's certain assumptions about beta, like, full support and like a lower bound on the proposal probabilities. This theorem isn't even going to withstand like infinite action sets. Yeah, so it's pretty rudimentary still, but I think, but not vacuous. And I think it allows us to at least show that this idea of composing missing data inference with reasonable objectives is viable, just as a proof of concept. Yep.
So one question when we learn the model is with respect to which measure we're optimizing the model here, which is not clear. So what is it here?
The surrogate. So it's, actually one thing I didn't explain is, pardon?
Over the context, but because the question is this the station distribution of the behavior policy, is the station target policy?
This is all one shot, it's IID. So there's no temporal dependence.
It's contextual bandits.
Contextual bandit. Yeah, I'll try to get to time a little bit, but yeah, it's like I said, it's beneath our attention. It's this problem way down there. But I think that we can see how we can do much better just by connecting up to things we understand from elsewhere. Yeah.
So where did you hide the strategy for completion of the missing data?
Yeah, it's in this like R hat. So everywhere you see an R, like a target vector, we're going to replace it with our estimated target vector.
And where do you account for the gap between the estimate?
Yeah, so in here, right, so there's a couple Jensen inequalities and then some tail, like, inequalities. Like, it's kind of buried in here. I have a write-up, like, I mean, we can go through it. I think it's more like I'm not trying to prove theoretical virtuosity here, I'm just trying to prove proof of concept and viability, that I think it is actually coherent. Probably the assumptions are pretty strong. Yeah.
So going on that last comment, so either according to your upper bound or maybe at least intuitively, do you have some way to estimate R hat which significantly improves upon just filling in zeros for the missing things?
Yeah, well, the doubly robust.
And anything else?
That's coming. But the theory isn't there for that. So. Yeah. Okay, maybe I'll move on. Yes. Okay, yes, so this is a composition of a trivial missing data inference strategy, which is this doubly robust estimator, right? We just exaggerate the differences of the predictions and the observed rewards, otherwise fill in our model predictions, fool ourselves into thinking that's the true reward function, and then applying the fully observed like loss functions. And then, the theory just kind of composes with that. Not too much work. Okay. All right, now, the other thing I want to observe is that if we really think hard about missing data inference, this is not a new problem, right, in machine learning. And the other thing is there's this weird kind of disconnect, another disconnect, which is the way we think about missing data inference in RL versus the way we think about it elsewhere. And I'll see how this goes. You know, one of the natural things to appeal to normally when we think about missing data inference is some kind of generative modeling approach, right? So usually when we're teaching classes, what do? We say, here's a graphical model, maybe it's a Bayesian network, and then here you've observed some of the variables in the model, and there's a bunch of variables you haven't observed, and then you formulate the posterior distribution over the things you haven't observed given the things you have observed, right? Just, you know, standard conditional, like, you know, distribution inference. You can apply that here, and so just as a simple, more concrete example, you know, a slightly more satisfying way to impute or make inferences about missing data is not just to kind of plug in, you know, some model guess, but to think, you know, what if we had some generative process like maybe some Gaussian or some parametric, you know, parameterized exponential family, where we have a generative mechanism that takes like the output now of our neural net, which could be, instead of direct guesses, like hyperparameters, for some exponential family distribution that accounts for assumptions about noise and so on and so forth. That when you see an observation like in a row here, right, we have some prior distribution over the reward functions in that context. We see that one observation, we get a posterior distribution over the, you know, the reward functions in that context, and we'll get a predictive distribution like a posterior expectation and so on and so forth. Now I'm just using Gaussians because this is of course one of the few cases where all the integrals are tractable and we get closed form results. But remarkably, even here for continuous action problems, you can use simple Gaussian inference, and it's not the standard approach right now, and I'm puzzled by this. So anyway, you can formulate like a prior over reward functions, you get a posterior over reward functions, and now you want to optimize the model, which is the neural net, which is, okay, let me explain it this way. I'm not saying let's go full Bayes and suddenly everything's an integral and then we're just chasing MCMC algorithms for the rest of the day. Imagine we just have this isolated sort of Bayesian inference only at the top layer of the network. The rest of the network is optimized just as usual. We're only using Bayesian inference to give us some more subtlety in the inferences we're making over the missing observations, okay? Even under some simple parametric assumption. There is an interesting question that comes out of this, and I think research directions that sort of accidentally spewed out of this. The natural way to optimize the neural network under, say, even this kind of Bayesian inference model would be, you know, classically empirical Bayes estimation, or maximizing the marginal likelihood of the observed data given the, you know, hyperparameters that we're producing from the neural net. So the neural net's like a big hyperparameter. We're just optimizing it to, you know, maximize log likelihood. In the Gaussian case, kind of somewhat embarrassingly, what we get is least squares regression, which not long ago I was telling you is a terrible idea, doesn't work that great in practice, okay? So actually empirical Bayes is a little more subtle, like it's least squares regression, but it's also doing some inference over the, like the variance scales. And so it does better than naive regression, but it's of the same type. But you can start to imagine like other reasonable sounding forms of optimization objective once we have some sort of Bayesian inference mechanism doing missing data inference. For example, a couple of things I tried was actually mapping it back to the surrogate objectives for the fully observed case, you know, where we were essentially looking at KL divergences between, say, a prior mean distribution and a posterior, or a posterior and a prior. Cool. The posterior prior direction is particularly interesting because it's also equivalent to a reasonable estimate of the mutual information between the latent parameter and the observed rewards. And we're essentially training the neural network so that if you could get zero training loss, you've removed any information dependence between the observed rewards and the latent parameter we're trying to identify, which means there's nothing left to learn from the data. Okay, and anyway, it sounds weird. We have no theory that justifies this yet. But actually it works, these were sort of the objectives that work, this one in particular, that work quite well in the previous scenarios. It actually also works quite well here and slightly better than classical empirical Bayes. Trying to figure out if this actually makes sense or if we're fooling ourselves. But it seems interesting. So this is at the intersection of both missing data inference and surrogate training objectives. Just a reminder, we have not lost sight of the fact that what we care about is expected reward, right? But just because we care about that, it doesn't mean we fixate on that as the only training principle. And it's just, you know, some graph. It's not as impressive as it sounds, but if you do like importance corrected expected reward maximization, some continuous action problem I don't have time to explain, you know, it's quite poor. And if you use the sort of, Bayesian, like empirical Bayes variance, you get substantially better. It's hard to see differences between the empirical Bayes variance in this example, but it turns out one of the KL divergences is slightly better than the others, totally empirical. There is no theory yet in place to justify this. So here's the appeal, which is a reminder that Bayesian estimation is a fine idea. It is biased, right? We've gone from fixating on variance reduction strategies for unbiased estimates to something that we know is a biased estimator. And it's therefore harder to analyze, but we also know has principles and support, for it that are not available for sort of simple importance corrected estimators. And another reminder, which I think is a healthy reminder for all of us, is like, Stein shrinkage. Admittedly simple scenarios, right? You can prove amazing theorems like if you do empirical Bayes estimation, right, for the mean of a multivariate Gaussian, you can get an estimator that's indeed biased, but has provably better expected squared prediction error than the unbiased, like maximum likelihood estimator, regardless of truth. No matter where the true mean vector is, right, you dominate the standard unbiased estimator. And so I actually see the open question here is, can we actually pull something like this off, even in a simple contextual bandit setting? Can we actually develop estimators, hopefully tractable ones, where we can actually prove domination, for example, in the expected reward that we produce? It doesn't seem hopeless. It's maybe not trivial, but that's just lying out there. I think that would be fun. Okay. And I'm going to use maybe 5 minutes, to explain that. Okay. Sequential decision making. So let's just pop up and say, okay, what if it's the same scenario except now it's the sequential decision making problem? What that means is the data is no longer like this simple matrix where there's a context you see single reward. Let's imagine it's like a replay buffer. We've just collected a bunch of trajectories, maybe like arm reaching trajectories or robot navigation trajectories, but just a bunch of natural trajectories where we've logged like here was a context, here was an action, here was the next context, and here was an immediate reward. Previously, I was quite astonished that we didn't understand how to extract good policies from such data. But now I'm not surprised anymore because I think we're struggling to understand how to do it when there's no sequence. But anyway, let's get our confidence back. So imagine now we're looking at these sequential trajectories and we want to extract a policy that's both empirically effective but perhaps also theoretically justified. What's getting in our way? And maybe I'll just say the most controversial thing now so I can have some conversations over the coffee break, which is I think the thing that's been getting in our way and has distracted us for about 30 years is the Bellman optimality principle. Now, we have a paper last year where we dive in deep into the nature of the Bellman optimality principle in the context where you introduce function approximation. And I think we should all know by now that those two things do not fit well together at all. Okay? And I think we finally achieved some level of understanding where we understand even algorithmically in simple scenarios what it would take to deal with Bellman sort of Bellman relationships or temporal consistency in value over time, and function approximation, and still somehow train the function approximator to converge to the optimal expressible policy. Not the optimal policy, and no guarantee about the relationship to the optimal policy, but the optimal achievable policy in your representation class with no other assumptions. And we've started to get on top of that. What it required us to do was to acknowledge that the Bellman optimality principle is the danger. Okay, so I'll just try to maybe explain why the Bellman optimality principle is not our friend. And then I've got a couple of bets, and then I'll end. So, we know Bellman optimality, right? Like the optimal state action value function or vector, right, is just satisfies an entire set of nonlinear constraints, right? So over the entire state action space. Now, this set of constraints is as big as the number of free variables, and it's nonlinear, which means a priori there's no reason whatsoever there should even be a feasible solution. Okay, it just so happens, right? The genius of Bellman's optimality principle is there is a feasible solution to this. There's guaranteed to be a feasible solution, but there's only one. The feasible set is a singleton, right? The optimal value function that is the only solution to this system of equations. Okay, and now we add function approximation. We all know what this means. It means that there is no feasible set anymore, right? Everything's infeasible. The chances of your function approximation class somehow magically going right through that one feasible point is measure zero. It's just not going to happen. Which means now we're engaged in this over-constrained system, and we've got to now make awkward trade-offs, like is this constraint more important than that constraint? How do we deal with this? Well, unfortunately, like a long, long time ago, we thought like, well, it's easy, right? You just add a penalty function. We'll just like square all those constraint violations and say, well, that's what we're trying to minimize. It makes whatever trade-offs it makes. And we struggle to do this. Then we take this objective, we pull a gradient through it, and we discover, well, we get this Bellman residual thing. We've got the double sampling problem. That's awkward. And then heroically, we can reduce that to this update where let's just neglect this and look at the update. This is no longer the gradient of anything. It's an update. And in the tabular case where we're not wrestling with function approximation, amazingly, this update can be proven to work. That to converge, if you iterate on this, you'll find fixed points, and the fixed points are solutions to this. But in the function approximation case, right, like the theory is mostly telling us it doesn't work, or it only works under very restricted conditions. Okay, I don't want to go through all this. So right now, we're kind of investigating 3 different attacks on how do you avoid any bootstrapping in, even in the batch case, from extracting an optimal policy without looking at Bellman consistency. Okay. Now, one, it's a bit of a cheat, which is building on our paper from last year, which is to go down the multiple hypothesis tracking path. So I think that the key observation last year is that if you really, really want to deal with the Bellman optimality principle under function approximation, and you want to do this kind of iterative update process, you have to track multiple hypotheses. That is, you kind of have to explicitly track all of the viable hypotheses that are consistent with your function approximation class and the max, and you'll discover like maybe the max decision is not consistent with the hypothesis, and so you have to kill that hypothesis and like back up a second max and so on and so forth. Okay? So we're trying to find practical algorithmic viable approaches that are built on this multiple hypothesis tracking strategy. I have some bizarre observations about like just distributional RL and why that might be working. It might also be about multiple hypothesis tracking. But one of the things I want to point out that surprised me and is Monte Carlo policy iteration. So this is, again, beneath us. It's this thing that's so trivial, it gets dismissed. Every time I mention it to somebody, they go, that can't work. And the idea is, what if we get rid of bootstrapping, but we have the Monte Carlo returns, right? We have the trajectories. So on the trajectories, we can do all the Monte Carlo inference. The Monte Carlo return is an unbiased estimate of the behavior policy value. Totally unbiased, it's of the behavior policy value. If we just took the Monte Carlo backed up returns and then optimize the policy to that, we're doing one iteration of policy improvement, right? You have a policy, you get a value estimate, we improve the policy, okay? That's pretty reliable. And it gets even better if you, like use reasonable surrogates and maybe some reasonable missing data inference mechanisms. And so this is just a toy data like cart poll, but I just want to point out that if you do random walk and cart poll, the poll falls over after 20 steps almost always. It's a very thin-tailed gamma distribution, like the chance of walking for 60 steps before falling over is almost nothing. If you just take those trajectories, you do Monte Carlo backups, and then you do reasonable policy optimization on it, you can virtually solve the problem, like just by doing even straight out importance corrected expected reward maximization. You can produce policies that keep it up for 250. If you now use like one of these surrogate techniques, you can now extract rewards that keep it up for 400. This is a huge gap, right? And this is the max trajectory witnessed in the training data. So you get this huge improvement gap, right, between what the data is showing you from the Monte Carlo returns and what we're able to produce. The reason I'm emphasizing this is what's going on here is the feature representation used here. It wasn't a neural net, just linear. It was just the coordinates, just the raw feature representation. The point I want to make is the raw feature representation generalizes wildly. And generalization is our friend. We want to generalize. You have very sparse data. We want to infer something from that data that we've got to apply in a much broader range of contexts. We want to generalize. But if you use that simple feature representation in classical techniques, anything that has to do with Bellman consistency, like Q-learning or any variant thereof, that feature representation, because it generalizes at a distance so wildly, destabilizes all Bellman backup-based techniques, like literally diverges. And what's gone on now for 20 or 30 years in RL is that the learning techniques and the feature techniques that are chosen to localize or not generalize value estimates to stabilize Bellman backups. Why are we learning to stabilize Bellman backups? We want to generalize. And these two things have been in opposition. And it's the commitment to Bellman consistency that I think has been holding us back, and pretty straightforward things start to seem viable if you just allow yourself to consider it. That's it. Okay, I think that's enough to say, and I'll stop there.
Summary slide. One question while Craig or you guys can both.
So you mentioned a lot of problem with the optimality equation. What do you think of the Bellman equation for policy evaluation?
Well, at least that one, is linear, like it's an affine. I mean, the other thing we know is that on-policy methods are, like by their nature, data inefficient, right? And it does seem crazy to take all this data and chuck it, or even correct it to be on policy. I'm not betting on that direction, but I'm not saying it's not reasonable or viable. I think that's another legitimate. So the things about like feasibility and so on and so forth, those questions are much easier in the outline case. Is that it?
Alex?
I guess just kind of being off of that. So I just wanted to first understand, when you say Monte Carlo policy iteration, you really mean doing like the bigger updates as policy iteration, but you're not just talking about something like reinforce, yes? Or I just wanted to understand.
Well,
reinforce, is it allowing big steps, or?
I want to just say yes, but actually I don't think that's right. So it is like reinforce, except that it's like reinforce where we're not using the reinforce, we're saying we want to optimize the policy to maximize expected return. Same as reinforce. It's just that we're changing two things. We're changing the optimization objective, and we're changing the missing data inference mechanism. You could think of that as one thing, but we're changing those two things. That helps. Reinforce was effectively that blue line. Now, this is also off policy, so by reinforce, I mean importance corrected, blah, 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 reinforce. So I would say, trying to do that, but use these other techniques.
And I guess by analogy to reinforce what I was going to also ask if your answer was yes, was that we know that we don't, at least normally in the on-policy setting, use reinforce as is. We do use these on-policy Bellman equations to reduce variance and so on. And so they should probably, I guess, be brought into the mix here as well, you would think, or?
Yes, it's that's a bigger side development to kind of organize that space. But so like TRPO or sort of prox things are reasonable. Like just from an optimization perspective, building a prox model or like a trust region is a sensible thing to do, almost independent of the objective. Like it's sort of an orthogonal consideration. Whether you want to get into soft actor critic, and we really do have a separate model, and we're interested in on-policy Bellman consistency or like temporal difference consistency. I guess that's kind of a side. Not sure. I'm not betting on that, to be honest. But that's legitimate.
Okay, let's thank the speaker again.